The Dance of Electrons. An introduction to electrochemical reactions. Electrochemistry describes a fascinating world of chemical reactions driven by electrons. These reactions are everywhere, from phone batteries to rust on metal. At their core, they involve the transfer of electrons between chemical species. Imagine a game of hot potato, but with electrons. Some atoms grab electrons, while others give them away. This exchange fuels the world of electrochemistry. Batteries and fuel cells rely on these reactions to store and release energy. Understanding these reactions helps us develop sustainable technologies. Redox reactions, a balancing act of give and take. At the heart of every electrochemical reaction lies a redox reaction. Redox describes the transfer of electrons from one chemical species to another. Think of it like a game of chemical tug-of-war. One player gains electrons, while the other loses electrons. The player who gains electrons is reduced, while the player who loses electrons is oxidized. These electron transfers drive the flow of electricity in electrochemical cells. Electrode potential, measuring the tendency to gain or lose. Now let's delve into the concept of electrode potential. This term might sound technical, but it simply describes how eager a substance is to gain or lose electrons. It's like measuring the enthusiasm of each player in our chemical tug-of-war. We can think of electrode potential as a measure of a substance's electron appetite. Some substances have a strong appetite for electrons, readily snatching them away from others. These substances have a high electrode potential. Others, however, are less enthusiastic about gaining electrons and have a low electrode potential. Measuring electrode potential is crucial for understanding how electrochemical cells work. By knowing the electrode potentials of different substances, we can predict the direction of electron flow and the voltage a cell will generate. This information is essential for designing and optimizing electrochemical devices, from batteries to sensors. Section 4. The Nernst equation. Predicting the force of electron flow. Imagine you have an electrochemical cell ready to power your device. But how do you determine the actual voltage this cell will produce under specific conditions? This is where the Nernst equation comes into play, a fundamental tool in electrochemistry. This equation, named after Walther Nernst, allows us to calculate the cell potential under non-standard conditions, considering factors like temperature and concentration of reactants. It's like having a magic formula to predict the strength of our electron flow. The Nernst equation provides valuable insights into how changing reaction conditions affect cell potential. It's used extensively in research and industry to optimize electrochemical processes for maximum efficiency. Understanding this equation is crucial for anyone working with electrochemical systems, from developing new battery technologies to analyzing environmental samples. Section 5. Galvanic cells. Harvesting electricity from chemical reactions. Let's explore galvanic cells, the powerhouses behind batteries and fuel cells. They convert chemical energy into electrical energy, consisting of two half cells with electrodes in electrolyte solutions, connected by a salt bridge, allowing ion flow. Electrons flow, powering devices from smartphones to electric cars. Galvanic cells revolutionize portable energy storage. Section 6. Electrolytic cells, driving reactions, uphill with electricity. While galvanic cells spontaneously generate electricity from chemical reactions, electrolytic cells do the opposite. They use electrical energy to drive non-spontaneous reactions, like splitting water into hydrogen and oxygen. Imagine pushing a boulder uphill. It requires energy input to move the boulder against gravity. Similarly, electrolytic cells use an external source of electricity to force a non-spontaneous reaction to occur. This ability to drive non-spontaneous reactions makes electrolytic cells incredibly useful for various applications. They are used in electroplating, where a thin layer of metal is deposited on a surface, and in the production of important chemicals like chlorine and aluminum. Electrolytic cells are essential tools for modern industry, enabling the production of materials and chemicals that would be impossible to create through spontaneous reactions alone.